We continued our discussions on second harmonic generation. Do you have any questions?
So you gave an example of a crystal in which K vector is at an angle psi m to z, and it is in a plane at some angle, and then Ex comes out to be Ei psi phi 1 and Ey is equal to E1 cos phi.
Yeah.
And then later you use
That's KDP, yes.
So I couldn't get from where do we get the psi m and the PNL after that?
No. What we did was, it was an example of KDP. So, if you recall, we need to propagate at some direction to the optic axis to achieve phase matching, okay? And that angle was obtained as an angle psi m with the optic axis. So, this is the direction of propagation of the fundamental wave. We also found out that for KDP, the fundamental wave at frequency omega is an ordinary wave, and the second harmonic will be an extraordinary wave for phase matching. So, I consider a general direction of propagation making an angle psi with the optic axis, with the projection of the k vector on the xy plane making an angle phi. Now, first of all, I know that omega is an ordinary wave. So, what will be the electric field direction of the ordinary wave going along this direction? Ordinary wave, it will have an electric field perpendicular to the optic axis and to the propagation direction. So, it must be in xy plane, and in the xy plane, if I project the y axis at the back, this E vector will be like this. This angle will also be phi, because this is the vector perpendicular to this direction and this direction, right. Then I get the electric field components along y and x, calculate the nonlinear polarization, and I find that the nonlinear polarization has only a z component. This nonlinear polarization has a component along the propagation direction and a component perpendicular to the propagation direction. So, the component perpendicular to the k vector will be responsible for generating the second harmonic wave along this direction. So, I take the sin psi m component of the total nonlinear polarization along the z component to calculate the nonlinear polarization that finally leads to my second harmonic generation. Okay, so that is where the sin psi m comes from there. Okay, yeah, Mohit.
Why is it necessary that we need the polarization to generate the further wave at 2 omega frequency in the same direction of propagation?
That is the direction in which I have phase matching. The omega direction, the k vectors of the omega and 2 omega, if they point in the same direction psi m, then only I have phase matching between the omega and the 2 omega wave. Otherwise, I don't have phase matching.
And what is the physical consequence of in extraordinary wave? We say that the energy vector, the pointing vector, points at a slightly different angle than the propagation vector.
Yeah.
So, how can we physically? I mean, how can we observe the difference? Theoretical analysis we can.
You mean the k direction and s direction?
Yeah.
How can we observe the difference between k vector and s vector?
Yeah. So,
I showed you the other day one picture for an acoustic wave propagating in a medium. So, if you take, for example, if you take an anisotropic medium and you launch a beam like this, okay. Suppose my optic axis is some direction here like this, optic axis, right. So, I am launching a wave in this plane. What will be the polarization state for it to be extraordinary? In this plane, right? Because the ordinary wave will be perpendicular to optic axis and the propagation direction which is in this plane, and so it will be like this. Ordinary, extraordinary is in this plane. So, this wave comes in with this polarization state. Now, what will happen is, okay, let me ask you a question. What determines the direction of the k vector as the wave goes from one medium to another medium? What should be conserved? Energy is all right. But for example, when a wave comes from one medium to another medium, the wave refracts either towards normal or away from normal. What is conserved in the k vector as it comes from one medium to another medium? Parallel component of the k vector. Please remember, S vector does not come into picture. It is a k vector parallel component which is conserved because you need to satisfy the boundary condition for all values of the coordinate on the surface. So, can you tell me, can you guess what will be the direction of propagation of the extraordinary wave, k vector of the extraordinary wave in this medium? Same direction, because the k vector, this is the surface, the component parallel to the k vector is like this, right? The component parallel to the interface is 0 of the incident wave. So, the component of the k vector of the refracted wave parallel to the interface must be 0, that means k vector must be like this for both ordinary and extraordinary. The ordinary wave has also its S vector like this. So, it will go like this, the beam will go like this and come out. The extraordinary wave also has its k vector like this, but because it is not propagating along the optic axis or perpendicular to the optic axis, its S vector is not parallel to the k vector. So, this beam may move like this. This is the direction of propagation of energy. Please note, if I draw the wave fronts of the extraordinary wave, it will look like this. The wave fronts of the ordinary wave is also like this. The k vector is always like this, but S vector is like this. And then what happens here? Please note, k vector of this is like this, and it will come out like this. So, these two beams will be parallel. What will be the polarization state of this? Perpendicular. This is the ordinary wave, this will be perpendicular. So, this is the component which splits the incident components, polarization components into two orthogonally polarized components, right. So, this beam, if you had an infinitely extended plane wave, you do not know where it is coming out from, you are not precisely defining a point on the beam. So, similarly, but to look at this, you need to look at a beam, and if you take a beam, the beam will propagate like this, and this is what I showed you in an image, two images by refringence. So, you will see, if you had a spot of light here, you will see two spots coming out, and if I rotate this crystal about this axis in this plane, this beam will rotate, this image will not rotate, right. So, and the plane containing this beam and this beam is the plane containing the optic axis. So, this is how I will visualize that I take a beam of a finite cross section, this is the cross section, the beam ordinary wave will move like this, the extraordinary wave will move like this at an angle, and that I showed you in a picture, one of these patterns which actually beam moves at an angle. Okay.
But if the incident beam was at an angle to the surface, then we have a splitting over there itself.
I need to make parallel component of k vector continuous, and I will have a Snell's law, the same Snell's law.
Because the refractive index is different for extraordinary and ordinary, you will have a splitting over there itself.
Over there itself, yes. The direction of k vectors itself will be different now for the ordinary and extraordinary. The ordinary wave will have its k vector parallel to S vector, the extraordinary wave will have its S vector even not parallel to its own k vector. So, there will be further refraction. So, I can actually, but Snell's law is simply the component of k vector parallel to the interface should be continuous. So, please note that if I apply Snell's law to the direction of the wave front, I have no problem, but if I try to apply the Snell's law to the S vector, I do not satisfy, because the incident ray is at a 0 angle and the refracted ray is a finite angle, it is not possible. But the Snell's law is for k vector. So, I can always use Snell's law to calculate the k vector direction of the refracted wave in the second medium, and once I know the k vector direction and the optic axis direction, I can calculate the S vector direction, which will give me the direction of propagation of the energy or the ray in the medium. Okay. Yeah, anything else? Okay, so let us continue with the discussion on nonlinear optics. So, what I want to bring in today is this concept of quasi-phase matching. QPM. So, one of the techniques that is used to achieve phase matching is birefringence phase matching, in which I use the anisotropy of the crystal. One of the waves is ordinary and the other wave is extraordinary. So, I use the extraordinary and ordinary refractive indices of the medium to achieve phase matching between the two waves. But the problem is there are many crystals like gallium arsenide, gallium nitride, zinc telluride. These are all cubic crystals which are isotropic, but are nonlinear. So, I can't use birefringence phase matching for this. Not only that, it may be possible that for a given set of wavelengths, I may not be able to satisfy this condition at all. As I showed you, there are some situations where the index surfaces do not intersect, then I can't use birefringence phase matching. So, what do I do with this? There are other techniques, and quasi-phase matching is a very, very important technique, which actually was proposed way back in 1962 by Blombergen and his group, and it is I will tell you what is the basis for this. Let us look at this equation again. dE2 by dz is I omega d by C n 2 E1 square e to the power minus I delta k z. So, if I solve this equation, we solve this equation assuming no pump depletion, which means E1 is a constant, and I got a solution for E2, and that contained a sink factor, and that sink factor is coming from here. So, my objective is to eliminate this term from the equation. One way is to make delta k is equal to 0, which is phase matching, normal phase matching. The other way is, now let me look at this following situation. Suppose I could generate a medium in which d was a function of z, a periodic function. So, let me take for example d0 sin kz, where k is equal to 2 pi by some period lambda, which means I am trying to look at a medium in which d goes like this. So, this is d as a function of z, d0 is the maximum value here, and this distance is lambda, periodic function of z, sinusoidal function of z. I will come to a little later how do I have a medium like this. So, let me assume that I could by some mechanism produce a medium in which d was periodically varying with z, d is equal to d0 sin kz. So, let me substitute into this equation. So, what happens to this equation? dE2 by dz is I omega d0 by C n 2 E1 square. Now, sin kz I write as exponential I kz minus exponential minus I kz by 2 I into exponential minus I delta k z. So, this is equal to omega d0 by C n 2 2 C n 2 E1 square exponential I k minus delta k z minus exponential minus I k plus delta k z. Now, I can solve this equation again with no pump depletion, which means assuming E1 is a constant. So, what will this term give me? This will lead to another sink function. You will get something like sin k minus delta k z by 2 by k minus delta k. Okay, let me actually solve this equation. So, this is simply if I integrate. So, if I integrate this equation, what will I get? E2 of z is equal to omega d0 by 2 C n 2 E1 square exponential I k minus delta k z minus 1 by I times k minus delta k minus exponential minus I k plus delta k z minus 1 divided by minus I times k plus delta k. Just the integral from 0 to z, and I am assuming E2 at 0 is equal to 0. There is no second harmonic in the at the incident plane, there is only the fundamental. So, I can express these two in terms of sine functions. So, let me write this equation. So, I get E2 of z is omega, let me write this like this, d0 by 2 by C n 2 E1 square. Now, I will get two terms. The first term will be exponential I k minus delta k z by 2 into sine k minus delta k z by 2 by k minus delta k by 2, right, because this is 2I. If I take this one of the factors out, this becomes 2I sine k minus delta k z by 2. The 2 I take it with the denominator here and write it like this, and then the second term will be minus. So, this is actually exponential minus I k plus delta k z by 2 into minus 2I sine k plus delta k z by 2 by minus I k plus delta k. So, this is actually omega into d0 by 2 by C n 2 E1 square into exponential I k minus delta k z by 2 sine k minus delta k z by 2 by k minus delta k by 2 minus I k plus delta k z by 2 sine k plus delta k z by 2 by k plus delta k by 2. Is it all right? Yes, Mohit, you were saying something? No, okay. If I multiply by z in the denominator now and the numerator, I get a sinc function here, there is another sinc function here. Now, look here, I have a sinc function or at k minus delta k. This capital K, remember, is the period, is the spatial frequency. Lambda is the period, capital K is called the spatial frequency, inverse of the period in space. If I choose capital K is equal to delta k, this will give me z. This term will still be very small, because capital K plus delta k will not be close to 0, it will be close to 2 delta k. This term will become 0, this k minus delta k can be made 0 by choosing appropriately capital K is equal to delta k. If I do that, this will become z, this will be some sinc function, this will hardly contribute to my E2, the main contribution will come from this term, and I will have some kind of a matching, phase matching. I have gotten rid of one of the terms, exponential I delta k z. What I have done is, I have by taking a sinusoidal dependence of d, I have converted the exponential minus I delta k z to a sum of two exponentials, and one of them I can make 1. If I choose capital K is equal to delta k, this is 1, this is not 1, and this 1 integrates to give me z. In fact, that is what is happening. And because capital K is in my control, if I can do this, if I can make a medium with this kind of a distribution of d, capital K is in my control, and given a delta k, I can choose a capital K to make capital K is equal to delta k, and this term will, then give me maximum contribution, and so what will be E2 of z? Then I can forget about the second term, saying that this will be very small, and I will have E2 of z will be approximately given by omega times d0 by 2 by c times n2 E1 square exponential I, okay, k is equal to delta k, so that goes off into, no, this is simply z. So, I am assuming k is equal to delta k. So, this is exactly like phase matching term. When the phase matching took place, I would have exactly got this, except that now I got d0 by 2 instead of d0 or d. The nonlinear coefficient has now effectively become half of the original nonlinear contribution because it is a sinusoidal variation, but it grows with z. It is not periodic, it is growing. So, the power in the second harmonic will now grow quadratically with z, at least for low conversion efficiencies, because P2 of z will be n2 by 2 c mu 0 mod E2 square into the area, and it will be proportional to all the factors. You will get exactly the same as before, except that d will be replaced by d0 by 2, that is all in the phase match situation. So, what I have done is, by having a periodic variation of the nonlinear coefficient, I have been able to overcome the phase mismatch term which is contained in exponential minus I delta k z. What is this capital K delta k? So, what is the coherence length? Pi by delta k. So, this implies delta k is equal to pi by coherence length, and for quasi phase matching, this is called quasi phase matching. For quasi phase matching, delta k is equal to k is equal to 2 pi by lambda. So, this implies the periodicity required is so if I periodically vary the nonlinear coefficient with a period which is twice the coherence length, I seem to be adding up the second harmonic power rather than periodically oscillating. Now, why is this happening? Let us see, let us try to understand. What happens at the coherence length? I had told you maximum efficiency, but the phase difference between the nonlinear polarization and the electromagnetic wave was becoming pi. So, if I have to do quasi phase matching, this must be the coherence length, because capital lambda is twice the coherence length. So, this must be the coherence length, twice the coherence length, 3 times the coherence length, 4 times the coherence length. What is phase difference of pi? Minus 1. So, let me try to plot now what is going to happen. If I look at efficiency versus z with delta k is equal to 0 with no quasi phase matching, it was going like this. This was the coherence length. Now, what is happening in this d? This d is positive for one coherence length, half a coherence length, sorry, this is twice coherence length. So, this is positive for one coherence length, negative for the next coherence length, next again positive. So, it changes sign every time you go through one coherence length. Magnitude is changing in between, but you change the sign. Change of sign means pi phase change. Nonlinear polarization is proportional to d. So, when I change the sign of d, I change the sign of nonlinear polarization. So, when the waves are propagating at this distance the nonlinear polarization and the electromagnetic field got pi out of phase, I forced them back in phase by changing the sign of the nonlinear polarization and bringing them back in phase. Again, in propagating through a coherence length, they will generate another phase difference of pi, and I bring them back in phase. Every time the nonlinear polarization and the electromagnetic wave get out of phase by pi, I force them back in phase by reversing the sign of d, which essentially changes the polarization by a factor of -1, because p nonlinear is proportional to d. So, when I change the sign of d, I change the sign of nonlinear polarization, which means I add or subtract a phase difference of pi, which means I bring them back in phase. So, what will happen now is, so what in the quasi phase matching case, the nonlinear polarization is changing sign every one of these distance. So, it comes here. At this point, if you did not do anything, the nonlinear, the wave at second harmonic would have gone down, but it does not go down, it goes like this now, because you have brought them back in phase. At this point, if you did not do anything, it would have gone down like this, but you change the sign again, bring them back in phase. So, every time the nonlinear polarization and the electromagnetic field get out of phase, you force them back in phase. If you did not, if you had perfect phase matching, it would have gone like this. This is delta k is equal to 0, this is delta k is equal to delta k, this is delta k not equal to 0, this is QPM, this is the perfect phase matching, and this is not phase matched. Note that the nonlinear coefficient is now down in this by a factor of 2, because the this is a similar equation to what we had written earlier, except that instead of d we have now d0 by 2. And what is d0 by 2? d0 by 2 is actually the coefficient of exponential plus ikz from here, except for an I factor, because d0 sin kz is d0 by 2 e to the power ikz minus d0 by 2 exponential plus ikz with a factor of 1 by I. So, d0 by 2, why is d0 by 2 appearing? Because when I wrote the sign in terms of exponentials, it actually that 2 factor came from this term. The sign is being written as a sum of exponentials, this 2 is actually coming from here, and this 2 is what is effectively reducing the effective nonlinear coefficient that is taking part, and that is the reason this is not rising as fast as here, it is much more slower, but the power is continuously adding. So, this is the principle of quasi phase matching, where whenever there is a phase change of pi between the polarization and the, which is the source, and the wave, I forcefully bring them back in phase. I do not need any birefringence for this. Now, remember what was the period we had calculated, coherence length we had calculated for the lithium niobate crystal, about 3.3 microns. So, I need every 3.3 micron the sign of d should change. So, this period is then supposed to be 6.6 microns, it is a very small period. Now, so the first question is, of course, how do I achieve this, and if I do not achieve exactly this, what is the result? Okay. Now, I want to draw the vector diagram and look at what is happening. Now, you see here is a situation where k at omega is here, k at omega, and k at 2 omega is not equal, is bigger. There is no phase matching, delta k is not 0. The the sum of k1 plus k1, 2k1 is not equal to k2. The length of this vector is k2, the length of each vector is k1. Propagation vector at omega frequency, propagation vector at 2 omega frequency. So, how much is this length? This length is k2 minus 2k1, which is capital K. A periodic modulation of the nonlinearity gives me a small vector in the momentum space. This is a drawing of momentum of the photon. There is an extra small element, extra small vector, capital K vector, which is coming because of this periodic variation, and that I am using to close this triangle, to close this figure here, and to make sure that sum of these three must be equal to this. Bragg diffraction of X-rays can be visualized like this. It is essentially, you have waves coming from here, you have a periodic lattice which has a spatial frequency vector that leads to coupling of this wave, electron waves or X-rays, into another wave in another direction. You can draw vector diagrams for X-ray diffraction, because it is after all changing the direction of the wave by giving extra momentum. So, the vector diagram for this is essentially that 2k1 is not equal to k2, but you have a small element which is left there, and that is what is being provided by the periodic variation of the nonlinear coefficient. So, quasi-phase matching is essentially a process in which you overcome the difference between k2 and k1 in this process, second harmonic, for achieving what is called as quasi-phase matching, that is overcoming this difference by a spatial frequency vector capital K. So, instead of the second harmonic periodically growing and dying, now the second harmonic grows, continues to grow, it has an upward trend, but of course, it is not as much as in the perfectly phase matched case, but at the same time it is growing. And today, this is a very, very important technique that is commercially used to achieve very high nonlinear effects even in media in which this was not normally possible. Now, in gallium arsenide, to convert a 10.6 micron wavelength, what is 10.6 micron wavelength? Which laser? Carbon dioxide laser. CO2 laser gives you 10.6 micron. So, I can do a second harmonic of 10.6 micron to get 5.3 micron. This comes out to be, this period comes out to be about 110 microns or so. So, what people have done is I make gallium arsenide, and by orienting the crystal appropriately, I can change the direction of the nonlinear term, the value of the coefficient. So, I take a set of gallium arsenide slabs of 105 micron thick, I rotate alternately like this, stick them together, and I have a beautiful quasi-phase matched crystal which works for second harmonic generation. There is no birefringence, but to do with 3 microns is not easy. So, I will tell you a little later what are the techniques used to generate this kind of a thing in lithium niobate, but first thing is, how do I do this? Okay. So, now in a crystal like lithium niobate, which is another which is a very important crystal, this crystal is ferroelectric. That means it has a spontaneous polarization at room temperature, and there is a temperature called Curie temperature. If you heat the crystal above the Curie temperature, it loses all its spontaneous polarization. So, when you come down below the Curie temperature, you need to orient the crystal by an applied electric field, and you can orient all the domains, and you can come down polarized. The crystal gets polarized again, just like magnetized media, your polarized media. Now, the crystal looks like this. Now, let me show you a plot here. there is an asymmetry in the positioning of the lithium, which is the small gray circle here, and the solid circles are the niobium atoms. And these three empty circles are all oxygen atoms, Li, NbO3. The lithium atoms can be above the oxygen plane or below the oxygen plane, both are stable situations. Because of this asymmetry, if the oxygen atom are sitting in this position, the spontaneous polarization is pointing up. If you displace the lithium into the lower surface below the oxygen plane, the spontaneous polarization reverses itself. Actually, this is just this one rotated by 180 degrees, it is the same. So, actually if you heat it to Curie temperature, the position of the lithium comes on the plane of the oxygen atom, and so there is no axis then, axis is just gone. Now, so what I need to do is this spontaneous polarization is connected to the coefficient of the D tensor and the axis of the crystals. So, what I need to do is to reverse the sign of the nonlinear polarization, I need to push the lithium ion across the plane below. So, but what I can have is then, suppose I have a crystal, I generate a crystal in which I have regions with the polarization pointing up, down, up, down. If I write this as my z prime axis, so in the z prime axis D will be positive, negative, positive, negative, like this, because in the z prime axis this is pointing up, so this is positive, here it is pointing down, so it is negative, it is pointing up again, positive, negative. So, in my laboratory coordinate system, this portion of the crystal will have a positive polarization, positive D vector, D component here, D tensor, there will be negative. So, it is essentially I have to understand what happens to the D tensor if I rotate my coordinate system. So, what is actually happening is the spontaneous polarization of the crystal is pointing up here, then down. So, this is what I have done is essentially instead of taking the crystals and stacking them together, if I can generate this where the crystal is made up of domains, here the domains are all pointing up, here the ferroelectric domains are pointing down, up, down, periodically. And if I do this period to be lambda, I will have a periodic variation in D. I do not have a sinusoidal variation, I have a periodic variation in D with a period lambda. Now what? Does it have a sign variation? I have to weigh a Fourier series. If I take a Fourier series of this, other frequencies will also be there. So, let me look at a Fourier series. So, let me take a D which is so this is sorry, this z axis is z prime axis is like this is a D value, okay. D is positive, negative, positive, negative. So, let me look at a D vector, a D tensor like this, okay. So, D of z, let me okay, let me draw a figure here and then write the corresponding. So, D of z is plus D for mod z less than L by 2. And is equal to minus D for mod z greater than L by 2 less than lambda by 2. Yeah, one second. This is D Z. Yeah, sorry.
So what is the purpose of this analysis? To find out the efficiency in such a case?
Yes. First of all, my question is, I do not have a sign dependence. I have shown you for a sign dependence. I cannot generate this normally because I can't vary the nonlinear coefficient continuously in a sinusoidal fashion. But what I can do is do this. periodic, plus minus, or in fact I can also do plus 0. I can kill the nonlinearity at some regions by doing some chemical operation, by diffusing ions or whatever it is. So, periodically I can kill the nonlinearity. I still have a periodic nonlinear variation. D varies periodically. What is important is the Fourier component, spatial Fourier component of that distribution. So, I want to just write an equation giving you the spatial frequency components of this.
So, but
Yeah.
to find out the efficiency,
Yes.
could I just not find out in the addition to E2 in one period?
Yes.
That will be proportional to Z,
Yes.
and then accordingly I can find out. Well, do I necessarily have to do this analysis to find out the efficiency? In a case where E1 is constant.
For example, I start from here. Okay. First I calculate over this distance, then I calculate over this distance, but please remember at this point there is both E1 and E2 incident. The equation which I have derived does not include this. So, I must calculate how E1 will vary when E2 is also present, although E1 remains constant.
We are taking the case where E1 remains constant.
E1 is remaining constant, but E2 is still present. Here is the situation with E2 of Z is not equal to 0. E2 of input is not equal to 0. So, the solution that you will get for E2 of Z with E2 is equal to 0 is not the same as you will get for E2 not equal to 0, and also depends on the phase difference.
So, it will be the same because dE2 by dZ depends only on E1 square,
Yes,
and that I am taking as a constant.
Yes.
The only variable here is D.
yes, but I have written E2 of Z minus E2 of 0 is equal to this thing, right. So, I have to, the next boundary condition becomes E2 of Z not equal to 0. Then I calculate from Z is equal to this value to this value, E2 of Z is increasing. So, E2 of Z will not remain this, E1 of Z from here to here will not be the same as E1 of Z increase from here to here.
So, it should
I mean, the approximation
should
we
be
are
the
taking
same.
that only. The rate of increase should be the same.
Okay, so, what will be your expression for efficiency, for example?
So, the increase that I have in the first half of the period
Yeah.
will be the same. The increase in E2 will be the same in the second half of the period, and so on in every half of the period. I'll have the same increase in E2 for as long as E2 is very much smaller than E1.
Okay. Yeah, it is. I'm even at the end I will be assuming E1 to be much or constant, almost constant.
Yes, sir.
Yeah.
So then we don't need this analysis.
Increase in E2, you are saying.
Yes, sir. The increase in E2 in every half period
Yeah.
will be the same because the slope is constant. Now,
Difference would be in the
Yeah.
final and the initial
so
value.
there is no really need for this analysis. Right?
What will be the effective nonlinear coefficient that is responsible for the increase? Suppose I give you a length L,
Yes, sir.
how would I calculate? Would I just divide by the length by the period?
I'll calculate the effective. Okay.
Huh.
I can divide it by the length.
I don't know, I have to check.
Okay.
I have to check whether if I divide L by the number of periods or number of half periods, will I get the same? I have to check this. I have not checked this, but what I will do is the following, that
Sir, over here, one more thing. We have assumed that if, so basically when I'm shifting the polarization,
yeah,
flipping it, what I'm doing is I'm rotating the crystal.
yes,
So when I do a transform on the D tensor,
yeah,
I'm assuming that the D tensor will become negative.
not all elements. I am assuming that the element that I am using in my nonlinear process is changing sign. Now, I will give this as a problem later to you. What happens if I have a coordinate system which is rotated at about one of the principal axes, which elements of the D tensor will change sign, which elements will not change sign. It is not necessary all elements of the D tensor change sign. Yeah. So, I am assuming here right now that this helps me to change the sign of the nonlinear coefficient that I am using in my nonlinear process.
Yeah. So the elements of the D tensor that actually contribute to the polarization,
Yes.
they should take change sign.
Yes. For example, if I in one of the example we had looked at, D33 was coming into picture. So, I need to make sure D33 changes sign. If D33 does not change sign in my process, then I have no use. Similarly, I can use D51 for some process. Does D51 change sign? So, that I must check separately. I am assuming that D changes, and it is only that changed D that I am using in my interaction process. Number one. Number two, it is not necessary the periods be equal. The duty cycle be half. For example, I will show you that it is not necessary that I change every LC. I can change every 3 LC.
Because the Fourier series will have that.
Yes, I will come here and then it does this, then it increases now much slower, because the Fourier series contains higher order spatial frequencies which I can use to phase match. Okay, so there is a first order quasi phase matching, third order quasi phase matching, fifth order quasi phase matching, because the period required here is much larger, 3 times, so 10 microns. But what is the price I will pay? The Fourier coefficient will be small, so the effective nonlinearity will be small. So all this I will get from this analysis. All I need to do is a Fourier series of this, and because as I showed you, the term which is actually cancelling this is exponential I kz. So that is assuming a sign variation, but this has many spatial frequency components. So mth, m times k will be responsible for cancelling this term, and I will get a single shot calculation of what is the effective nonlinearity, which is helping me, and whether that Fourier coefficient, if it happens to be 0 here, there is no effect. That nonlinearity is absent in my system. Okay. So let me leave this problem to you. Simple Fourier series. So this is my function as a function of z. So assume d of z is equal to d times sigma gm exponential I m k z. Fourier series in terms of exponentials, not sine cosine. Calculate gm. So let me give you the expression 2 by m pi So gm is the mth Fourier coefficient corresponding to the spatial frequency mk. So the first term will be, if I use m is equal to 1, it will be 2 by pi, and if I use L is equal to half lambda, which is a 50% duty cycle, this figure which I have drawn is a 50% duty cycle. This is equal to this. Here I have drawn a figure in which L may be different from lambda, half a lambda. So if I take L is equal to lambda by 2, if I take L is equal to lambda by 2, which is the duty cycle of, not L is equal to lambda by 2, yeah, L is equal to lambda by 2, right. Then G1 will be 2 by pi, what will be G2? What is the value of G2? So let me write here, G1 is equal to 2 by pi, G2 will be yes, G3 all even coefficients will be 0. So if I were looking for using minus, okay. Anyway, the nonlinear, you see the effect. So this d becomes a sum of various exponential terms. The minus sign will finally not matter in my, because it's d square proportionality. But otherwise, anyway, there is a minus sign. So if I use this term, if I use this Fourier coefficient for my quasi phase matching, it's called first order quasi phase matching. I can use this term G3 for phase matching, it's called third order quasi phase matching, fifth order quasi phase matching, and so on. If I want to do second order quasi phase matching, what should I do? I must change the duty cycle. Lambda L by lambda I must change. Now I leave this problem to you. What is the best L by lambda that I will choose to make G2 maximum? Not maximum among them, but G2 should not be 0, but the maximum value that I can get if there is a periodic variation in D. What should be the value of L by lambda so that G2 is the maximum value? Okay, I leave this problem to you, please work it out. Okay, so I think we will stop for the quiz. So what is interesting is that I can use a periodic variation in the nonlinear coefficient to compensate for the phase difference that exists, that generates as they propagate. and bring them back in phase. Every time they get out of phase, I bring them back in phase. Okay, so we will now close here and we will have the quiz. Okay, this is a crystal with a finite nonlinear coefficient d, and waves at omega 1 and omega 2 are incident in the crystal. The propagation constants are k1 and k2. So, because of this nonlinear effect, there will be nonlinear polarization at the new frequency omega 3, which is omega 1 plus omega 2. What is the velocity of this polarization? Because I would need to know this to understand phase matching. So, what is the velocity at which this nonlinear polarization at omega 3 frequency is propagating?